Hello, my name is Shawn Prem Benjamin, and I'll be presenting on the topic application of finite automata in network. First, what is a finite automata? A finite automata or a finite state machine consists of a finite set of states which can transition to which it can transition to depending upon the input value. Considering this string over here, this is just a normal state transition diagram for checking how many number of zeros, how many number of ones are present. There are two types of finite states: a deterministic finite state machine and a non-deterministic finite state machine. It can also be called as finite automata. Now let us see at some difference. In a DFA, every single alphabet set element must be represented in each state. And there is only one state transition for each alphabet in a particular state. Whereas in an NFA, it can have any number of states with any alphabet from the alphabet. Sometimes it doesn't have to show transitions for all of the alphabet set elements. Obviously, DFA will be more efficient than an NFA. But a DFA cannot have null transitions, whereas an NFA can have how many ever null transitions that it wants. On to the application. These are only a few applications that we'll be covering in this paper. There are many more other applications. Some of them which we'll be following today are pattern matching, firewall rule processing, network protocol passing, stateful packet processing, network traffic classification, optimized packet formatting, intrusion detection system, load balancing, scalability, and efficiency. Now let us go to the first one, pattern matching. Now we all know that DFAs are usually used to validate a string to check if there is a certain pattern either at the beginning, end, or at the middle. We will be using this exact same concept in network. We'll be checking if a packet has a certain number of trailing zeros and ones, usually in its header or its trailer. If it has that certain number of zeros and ones, sometimes will be accepted. Sometimes, if that is not the pattern for this particular network, it will be rejected immediately. The second application is we can use DFAs to check if it follows the firewall rules of a particular network, server, or the system. Each and every network will definitely have some rules and regulations that it has to follow, which is set by the firewall. If a particular packet does not follow these firewall rules, it will not be accepted. Here, in a DFA, we can assume each state to have a particular rule of the firewall. If it follows all of the rules set by the firewall, that is passed through all the states and goes to the final state, it is accepted into the network. Else it is dropped, assuming that it is a malicious packet. On to network protocol pass. Now let's say that your packet does go through your firewall. It will have to check what kind of protocols that it is following, because we can't use HTTP in HTTPS, like similar to that case. Assume this finite state machine over here. It is checking if there is host present at the beginning. Usually, every network protocol is placed at the beginning of the packet. So we can create a DFA where it can go to various different protocols depending upon what's at the beginning of the string. Also, certain networks may not accept certain kind of network protocols. So even if it does go through the firewall, it'll have to check through these protocols which are present in the system, if it can be accepted. Keeping in line with the title of firewalls, SPI, that is stateful packet inspection, is another firewall technique that inspects the validity of a packet. Here, similar to what we have done previously in the firewall, the DFAs usually have logic of the SPI technology firewalls as its various states. If it follows all of the rules and regulations set by the SPI, then it gets accepted. Suppose there's an outside source which is sending a packet. The SPI firewall, that is stateful packet inspection, will check each and every detail of the packet to check if it follows its meticulous set of rules and regulations. If it does not, it is immediately dropped, assuming it is malicious. DFAs can also be used for network traffic classification. Suppose your network is sending various signals. That is for various types of protocols. As discussed before in the previous slides, we can use DFAs to separate the kind of signals and protocols which is being transferred. We cannot watch a video in a text reading app, can we? So this helps us to segregate the network traffic properly so that there are no interference in the network, making it much more easier for the users in the network and making the network much more secure. Now, of course, in a network, there will be routers through which packets can be sent. It can be sent from various networks to another using these various routers. We can use DFAs here again to check if it is valid to pass through using the bits of either the header or trailer or the packet. If it does not follow it, it will not be accepted. Also, it can also be used to check for the shortest route that it has to go go from sender to receiver. In networking, we use a certain concept known as handling code to check if a packet is valid or not using either its header or trailing bit. If it's valid, it gets accepted. Else, it is dropped as a malicious packet. Here we can again use DFAs to check if this particular string of bits is following a certain pattern set by the network. If it does not follow it, again it gets dropped as a malicious packet and it gets rejected from getting into the network and affecting the user's device. Similar to the previous topics which we have talked about, when we come to the topic of load balancing, DFAs can have particular states corresponding to particular servers, which have its own rules and regulations on what kind of packets it can accept. And the packets go to the server whose rules it follows. Now, when we make a network, we may plan to scale it up. That is, add more users into the network, or maybe add another separate network entirely, or more routers. Here, using all the previous concepts, we can easily scale up the network and increase its efficiency. Since the DFA already has pattern recognition, it can choose which routers it needs to go through. It can check to its firewall and SK firewall protocols. We can use it easily to expand and make it more efficient. On the topic of scalability, if we want to add more routers of server, it is very easy. We just need to add a few more states into the DFA, shifting the final state to a little bit more farther away. Now, what do we learn from all of these applications so far? I've just been showing these slides. From this, we understand that DFA is a machine that can recognize patterns, either at the beginning and or middle again. And we can implement this exact same logic into a network. A network is just a big if-else loop, checking a statement at each step if it follows certain rules and regulations. This is why DFAs can be easily used in networks, making it much more efficient and much more safer for the user. This concludes the presentation. Thank you for watching.